So let's say you've located a point of discontinuity on a function. How do you tell whether or not that discontinuity is a removable discontinuity? Well, that's the subject of this video. So we've covered in a previous video that a discontinuity on f of x at x equals a is deemed removable if there exists a continuous function, capital F of x, that's identical to lowercase f of x except at x equals a. If there exists such a function, then lowercase f of x is said to have a removable discontinuity at x equals a. We've also covered the two scenarios in which lowercase f of x has a removable discontinuity at x equals a. The first one is which you just have a hole at x equals a, so the function's not defined at x equals a. And the second one is the function is defined at x equals a, but not where you'd expect it to be. But in either case, notice that the limit of f of x as x approaches a exists. So the left and right limits are equal. So as we approach this value from the left and the right, we're really, as we approach a from the left and right, we're approaching the same function value here. And that function value is where this hole is. And in this case, this is the same deal. As we're approaching x equals a from the left and the right, we are approaching the same function value. The only difference is right at x equals a, the function value is different. But we're still approaching the same value. Now in either case, we can make this function continuous by redefining the value at a. In this case, a is f of x is undefined at x equals a, so if we just define it equal to this limit here, then we'll have a continuous function. In this case, if we redefine f of x at x equals a equal to the limit, then we will have a continuous function. So again, to drive the point home, the limit as x approaches a of f of x exists in both of these cases, and that's because the left and right limits are equal. Remember the three criteria for continuity or that the limit exists, so the left and right limits are equal. That's criterion. That's one of them. The other is that the function value exists, and the third is that the function value and the limit are equal. So to make either function continuous, we just have to define f of a, so the function value at a, so that it equals this limit here. But really, as long as this limit as x approaches a exists for the function, we know we're dealing with a removable discontinuity, because all we have to do is define the function at that point so that it's equal to that limit. Or in this case, like redefine the function value so that it's equal to the and if the limit as x approaches a of f of x does not exist, then we know we're dealing with a removable discontinuity at x equals a. So say this is f of x here. And this is the point of discontinuity at x equals a. Is this discontinuity removable or non-removable? Well, we ask ourselves, does this limit exist? Does the limit as x approaches a of f of x exist? And it does not, because the left and right limits are not equal. What about this case in which we have a vertical asymptote at x equals a? Is this discontinuity removable or non-removable? Well, the answer is that it is non-removable, and that's because there is no value that this function is tending towards as x tends to a. It's going up toward, it seems to be just creeping up towards a positive infinity, and that's not really approaching a value, because infinity is just a concept, it's not a concrete number. So here's an example. Is the discontinuity of f of x equals x over x plus 3 cubed at x equals minus 3 removable or non-removable? Well, this involves a vertical asymptote at x equals minus 3, so and in general, vertical asymptotes are non-removable discontinuities. But if you didn't know that, how would you answer this question? Well, you look on either side of x equals minus 3 and see where the function is heading. So for example, if we looked at numbers just slightly smaller than x equals negative 3. So say x equals negative 3.0001. Well, then what's f of x? It's going to be f of negative 3.0001. And that's going to be negative 3.0001 over negative 0.0001 cubed. So, and this is really just going to be a very large positive number because we have a tiny negative fraction cubed. It's going to be when we cube it, it's going to become an even smaller negative fraction. So this is going to be a huge positive number. So this is coming in from the left, right? So say this is x equals minus 3, and we're looking at negative 3.0001. So we're looking somewhere here, and it's going to be a huge positive number. Now what about, say, x equals negative 2.9999? So on the other side of x equals minus 3. Well, again, we'll look at f of negative 2.9999. It's going to be negative 2.49s here, divided by positive 0.0001 cubed. And we have a negative number very close to 3 over a tiny positive fraction. So we're going to get a huge, a negative divided by a positive, a tiny positive fraction is a huge negative number. So, I mean, clearly coming in from both sides, we are not approaching the same number. In fact, we're not really approaching anything. We're coming in from the left, we're tending towards positive infinity. Coming in from the right, we're tending towards negative infinity. So we know that this discontinuity is non-removable because the limit coming in from the left and right are not equal. Even, let's say, for argument's sake, let's say both of these were positive infinity, we would still have a non-removable discontinuity because we're not tending towards a particular number and the same number from both sides.